Okay, so the question was on, n-level density. So let me just quickly introduce L functions and the statistics, and then I'll circle back to your question. And if I'm not going into enough detail, let me know. So hopefully you've watched the two videos right now. The object that we start studying is the Riemann zeta function here. So this is the simplest L function. The coefficients are always just 1 in the numerator and then n to the s in the denominator. More generally, instead of having 1, we could have some other numbers over here. We'll always assume there's some kind of product. This is called the Euler product. And we write it as a product over primes of something nice. So here it's 1 minus 1 over p to the s inverse. More generally, we have some function that depends on p. And there's supposed to be a functional equation relating its values at s and its values at 1 minus s. If you look at a more general L function, we still have something like that. Depending on how you define things, you might have not s into 1 minus s, but s into 2 minus s. You can always renormalize and adjust things so that you can always deal with s into 1 minus s, but you need to be aware of this when you look at things in the literature. Other people may have things defined for the elliptic curve L function as s into 2 minus s, and there then the center of the critical strip is not s equals 1/2, but s equals 1. So the Riemann hypothesis, or the generalized Riemann hypothesis, is all the non-trivial zeros have real part of half. We talked about how last time, because of the gamma factor that emerges, there are trivial zeros at the negative even integers. And the observation, which is the starting point of the story, is that the spacings between zeros of the Riemann zeta function, or more generally of other L functions, seem to be the same as what you would see between the eigenvalues of complex Hermitian matrices, and similar behavior was seen looking at energy levels of heavy nuclei. There, however, instead of complex Hermitian, you saw real symmetry. And so one of the most beautiful figures you'll ever see in mathematical physics, here are 70 million consecutive spacings of zeta starting at the 10 to the 20th zero. So again, you might think that this is fairly impressive, and it is a highly non-trivial calculation, but 10 to the 20th is still a very finite number. And it is possible that the limiting behavior has not yet sunk in. We don't think that's the case, but you always have to be careful when you see something like this. So there's a tremendous fit between the spacings between zeros and the Riemann zeta function side and random matrix theory. You can look at the differences and look at the lower order terms, the fluctuations, and there's a decent theory about that as well. But right now we're concentrating on the main term. So far from a proof, but a beautiful numerical observation. And we talked a little bit last time about how you might get something like this using contour integration of the explicit formula, so I'm not going to go through that again. And we got these wonderful formulas which relate sums over zeros to related sums over primes. And the hope is that by understanding the sums over the primes, we can deduce information about the zeros, or conversely, if we know things about the zeros, we can use that to get information about the primes. And so lots of different versions of the explicit formula for different families. And now let's talk a little bit about the spacing statistics that one can look at. So the first is the n-level correlation. So looking at how many times do we have a tuple that lies in a box. As you go further in number theory, you learn that it is absolutely a nightmare whenever you have a hard cutoff function. So a hard cutoff function is disastrous in terms of actually calculating things. So instead of using a box, it's frequently better to use a smooth test function. And if things cut down very quickly, this is more than enough. All right. So the simplest is we have some sequence, alpha 1, alpha 2, alpha 3, ... And let's assume they're in increasing order. One thing we have to be careful about is that if the spacings between them is growing, it could become a little bit of a challenge. So you might adjust things, so you might normalize to have, average gap of size 1. So for example, if we look at the primes, you get 2, 3, 5, 7, 11, 13, ... and you get as gaps, 1, the lone odd number, you would have 2, 2, 4, 2, and so on and so on. So pi of x is the number of primes p less than or equal to x. It's approximately x over log x. So if p is of size x, next prime is at approximately x plus log x. So you might study not p, but p divided by log p. And normalizing something like that, you now have a sequence where you might have the gaps to be of size 1. For the Riemann Zeta function, if s is equal to 1/2 plus it, next 0 is about 1 over log t away. So look at multiplying by log t to basically to unfold, to spread things out. Okay, does this make sense? Because if we didn't do this, if we wanted to study, how often, alpha I minus alpha k is in an interval. So this would be the 2-level correlation. How often are there 2 zeros whose difference is in an interval? Well, if the sequence is just naturally, growing, so that the gaps are just getting larger and larger and larger, what would you expect this to be in the limit?
Infinite.
Say that again?
I think he said zero.
So I couldn't hear what you said. So how often would you expect this difference to be in a fixed interval, a finite interval? If we have, for instance, the alphas of the primes. So we want to calculate what fraction of the time, so if we're doing the 2-level correlation, we would just have alpha j1 minus alpha j2. We would count the number of pairs of, j1 and j2, where j1 and j2 are distinct, that lie in some fixed interval, and then divide by n. And we'll,
Yes, so it would be super unlikely. So I think Henry put in the chat probability 0.
yeah, it would basically be 0. So we wouldn't expect this to happen at all. And so when you talk about primes, you don't really want to talk about a fixed gap size. Well, you do, but that's extremely hard. What you want to do is you want to talk about gap sizes relative to the average gap. This is why trying to prove that there are infinitely many twin primes is so hard, because that spacing is almost 0 relative to the average spacing. The average spacing of primes of size x is about log x. And so you want to know how often are the normalized gaps in such an interval. And this is a great statistic to look at. And you can look at it for a variety of different quantities. And it turns out, if you know the n-level correlations, essentially for any box and for all n, you can use that to deduce the spacings. And so if I look at my sequence, my normalized sequence, I have, alpha 1, alpha 2, alpha 3, dot, 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 dot. And I want to know how often is alpha j1 minus alpha j2 in some interval I with, j1, j2 less than or equal to n. And I want to count. It doesn't say anything about these being adjacent. And so there's a lot of inclusion exclusion going on. You know, I really don't want to go into the details, but the idea is if you know the n-level correlation for everything, then you should know it for not just the n-level correlation, but the actual spacing function, that you should be able to deduce n-level correlations imply the spacing distribution. Okay, so this was a exciting result when it was discovered that there was, you know, so much similar behavior in these very different systems. And then here's a collection of results. So Odlyzko looked at the normalized spacings of Zeta S and found phenomenal agreement with complex emission matrices. Montgomery showed that the two-level correlations, the pair correlation for the zeta function, agreed with this random matrix theory result for suitably restricted boxes. And then Dennis Hetchel proved the three-level correlation also worked. And it was not easy to figure out what's the right statistic to study. How do you generalize this? How do you do the combinatorics? Around the time Hetchel was doing this, Rudnick and Sarnak proved not just the three-level, but the n-level, and not just for zeta, but for all automorphic cuspidal L functions. And so the word all is absolutely amazing. So what's going on is even though the L functions behave a little bit differently, there is something going on that's responsible for this universal behavior. And so when you look at the quantities that arise, it turns out that the coefficients of the L functions have certain distributions. And those resulting distributions have certain quantities that arise. And even though they may have different behavior, the things that get fed into calculating the correlations, you only care about certain quantities, and those are the same. So for example, if you know probability, you could have lots of different probability distributions that have a standard deviation of 1. They could have many different shapes and still have a standard deviation of 1. And if all that matters is that the standard deviation is 1, then differences in behavior don't really matter. And that's essentially what's going on. And then a little bit later, Katz and Sarnak noticed that the n-level correlations are the same for all the classical compact groups as well as the complex emission matrices. So when you say that it agrees with the complex emission matrices, you could have said it agreed with these classical compact groups as well. And so now the question becomes, what's the true statistic to look at that really describes what's going on? Well,
I had a quick question.
Yes.
So when we're talking about like this box B that the increasing sequence, like those differences are contained in,
Yes.
when in the work of Sarnak, did they like pick specific boxes B, or like I'm not entirely sure what the result was?
You want to basically be able to do this for an arbitrary box.
Okay, so what they did is
the idea is the more boxes you can do this for, the more you can sniff out what's going on.
Okay, so what they did was basically they were able to take any increasing sequence in this situation, like of the zeros, and tell us information about how many of them are contained in a box, like the density of those spacings?
Right, they were able to calculate these limits. And then if you knew these limits for any box, you would be able to deduce the spacing gaps. They weren't able to do this for any box. They could only do this for certain boxes, and they smooch things out. But at the highest level, if you could do this for any box, you would then get the spacing distribution. And that's what people really want to know, the gaps between zeros.
And for the box, why is it in R to the n-1 rather than just n?
Well, because if you look at it, if I have my sequence of n numbers, I'm going to have n-1 differences the way I've got things defined. 2 minus 1, 3 minus 2, n minus n-1. So when I take n elements, the elements are not necessarily in increasing order at this point. I'm just choosing n elements randomly from my alpha sequence. That's why I have j sub 1, j sub 2, and so on. And so when I have my n elements, it gives me n-1 differences.
So I had one more question. So I guess why do we care about okay, maybe different question. Is in some sense 3-level density more restricting than 2-level density then? Because you're considering more zeros in a sequence?
So if you want to understand the 3-level density, I mean, to some extent, you can view each component individually.
Mm-hmm.
And so, I don't want to get too much into this because this is not really going to be what we're going to look at. And this is the range of always how much we want to go into. So let's say we have, alpha J1, alpha J2, alpha J3, and we have some box B, which is say I1 cross I2. So we would have alpha J2 minus alpha J1 is in I1, and then we would have alpha J3 minus alpha J2 is in I2. So we would be studying these problems simultaneously, okay?
Okay.
Imagine I1 equals I2 and it's symmetric, about 0. Okay? In this case, if we take J3 to equal J1, we would actually just reproduce the 2-level density, because this would just be the negative of that, right?
Yeah, I think you meant to write J3 equals J1, but yes.
Oh, sorry. J3 equals J1, thank you. And so if you look at the conditions we have over here, we don't want any J1 or Ji to equal Jk. If we do something like that, we could actually reduce to something that is a lower level. And so sometimes what you do when you have a condition like this is you might do inclusion exclusion, because it might be technically easier to study everything. And so over here, if I allowed J3 to equal J1, if I1 equals I2, if I have a symmetric box, especially one that contains 0, I'm essentially just getting a 2-level lying inside. And so it happens, we get a 2-level lurking inside. You can remove with inclusion exclusion. So again, when you're looking at the explicit formula, it's much easier to use the explicit formula to sum over all zeros, not over all distinct zeros. So what you frequently do is you sum over all zeros and then you remove the contribution from the repeats. And you'll often have things going back and forth, back and forth.
Okay, that makes sense, thanks.
Yep. Okay, so the main thing is that these n-level correlations, and again, we're not going to spend too much time on them, is insensitive to any finite set of zeros. Because if you look, we're dividing by n because things are growing, and I've normalized to have, say, mean spacing 1. If I fix 1, 0, eventually everything else is going to be so far away from it that it's not going to really contribute anything to this limit. So these limits are insensitive to any finite number of zeros. In particular, they're insensitive to what's going on at the central point, which is the place where all the action is happening for the L function. So unfortunately, the n-level correlation is completely useless at the one point we want to know the most information. So we need a new statistic. And the new statistic is the n-level density. And so the idea is to take some even Schwartz functions. They don't all have to be the same. And again, this is a little bit restrictive. I'm looking at a function x depends on n variables, x1 through xn, and I'm assuming my function factors as a product of individual functions. You lose a little bit of information like this. The more general case would be it's phi of x1, x2, x3, dot, 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 xn. But, this is good enough for a lot of things. And what we'll do is we take distinct zeros and we rescale all of them by the analytic conductor so that the mean spacing near the central point is now 1. And we evaluate our Schwartz functions at these and then we sum. The word distinct is painful because the explicit formula involves sums over all zeros. So what you do is you start playing, inclusion-exclusion games. So if I have come back to here, if I put this in, how do we deal with distinct? What we could do, for the 2 level, you sum over all zeros and then subtract J1 equals plus or minus J2. We have to do a plus or minus because these zeros are symmetric they're symmetric on the central line, on the line real part of S equals 1/2. So one way to do this is you would then subtract J1 equals J2. Well, if you have, say, J1 equals J2, and again, I may be off by factors of 2, I don't care, you'd have something like the sum over J of phi 1 of L F gamma F J1 phi 2 L F gamma F J2. This is the same as the sum over J of a new function phi 1 phi 2 at LF. Oops, this should be a J1. Gamma F of J1, which is a 1-level density. So we can extend the sum to being over all zeros, and then we basically subtract a 1-level density, not with test function phi 1, but with test function phi 1, phi 2. So it's not a big deal to have something like this. Okay, so returning to the slides, what's nice about this is the individual zeros can now contribute in the limit. And in fact, most of the contribution is going to be from the zeros near the central point. So whenever you see a function like this, always think of maybe a Gaussian, which has extremely rapid decay. And so the biggest contribution would be from zeros at the central point where gamma f is 0. I'm running the zeros as 1/2 plus I gamma of f. And then as I get further and further away, the contribution is going to be smaller and smaller and smaller. And then the hope is that if we average this over similar curves, we're going to get something very nice. And this is a key point. And this is one of the biggest differences between the n-level densities and the n-level correlations. So for the n-level correlation, here's 0, here's 1, here's the line 1/2. I have my zeros, symmetric. But as I go very, very high up, I get a lot of zeros close. Average gap is 1 over log t if you're at height t. So as you go higher and higher up, you have lots and lots of zeros nearby. So one L function So one L function is enough for averaging. So we always need to do averaging in mathematics. If we do the n-level density, it's very different. Here's 0, here's 1, here's 1/2. And now, we care about what's going on near the central point. And we can normalize or renormalize to mean spacing 1. but you only have a small number of zeros near the central point. And so because we only have a small number of zeros, we need to average over similar L functions. And again, we need a large number of objects. Over here for the n-level correlation, we have so many zeros in a small interval as we go high up that we're good. Over here for the n-level density, we don't have that many zeros near the central point. So we're going to have to average over a bunch of similar ones. And then what Katz-Sinai conjectured is that for a nice family of L functions, the n-level density depends only on a symmetry group which you can attach to the family. It behaves like either unitary, symplectic, or orthogonal matrices. And so more explicitly, we calculate the n-level density for fixed L function f. So we do this calculation. Then we average over f in a family. So we sum over all f in a family. And then we divide by the number of elements in the family. And the hope is that this converges to something nice, to basically integrating our test function phi against some function that we can associate to the family. And so for the one-level densities, here is what you would explicitly calculate for what the one-level densities are. And the important thing to note is that unitary, symplectic, and orthogonals, the three orthogonals are indistinguishable if the support is less than -1, 1. So for functions whose Fourier transform live in -1, 1, whoops, these three all look the same. And the reason is eta is equal to 1 if the absolute value of u is less than 1. So this would be -1/2 plus 1 is 1/2, 1/2, and again 1/2. So you can't distinguish between the three orthogonals if the support is small, but you can tell the difference between orthogonal and symplectic and unitary. If you look at the two-level, arbitrarily small support for the two-level works. Our goal is to try to calculate these expansions and show agreement between L function zeros and random matrix theory for as large of a support as we can. And the way these are calculated is from determinants of classical compact groups. The calculations are a nightmare. And so we're going to look at later another approach. And so I want to just end today with an interpretation of what's going on. And so the interpretation is, the similarities between L functions and heavy nuclei. So I'll just take a quick snapshot. Okay, so here is the similarities. So in the physics side, you want to understand the energy levels of a heavy nuclei. So, here is your nucleus, and you want to understand it. So one of my favorite quotes in physics is, if you want to understand a grandfather clock, what you do is you take two grandfather clocks, accelerate them to almost the speed of light, have them smash into each other, and then you look at all the stuff that comes out, and from that you somehow deduce the internal workings of a grandfather clock. We take our atom, or nucleus, and what we do is we shoot neutrons into it. And then we see what happens. Now, we would love to shoot a neutron of arbitrary energy level into this, but we can only shoot neutrons in certain energy bands. And from that limited information, we try to deduce what comes out. In number theory, it's very similar. Instead of energy levels, we have zeros. In neutron, what we have our Schwartz test function. And the explicit formula relates these sums to what we can understand. And then the restriction of we can only shoot neutrons of a given energy level becomes we can only do the calculations if the Fourier transform has a certain support. You may have actually seen something similar to this. Imagine I tell you we have a function f and the integral of -infinity to infinity of f of x, g of x, dx equals 0. for any continuous differentiable function g. What would you like to conclude about f?
Maybe where f is non-zero?
I'm sorry?
Maybe where f is non-zero?
Well, I'm saying, I'm giving you some function f, and I'm telling you that when you integrate f against any g that's continuous and differentiable, you always get 0. What can you deduce about f?
My gut says f is 0 everywhere, or
Okay.
that it's an odd function, but I'm not sure.
Well, but I'm saying it's for any g.
Yeah, okay, then it's 0 everywhere.
So what are you assuming about f when you make the statement that f is 0 everywhere?
Could it be 0 almost everywhere? Because it could
Well,
be,
assume f is, what kind of function do you want to look at first? Let's assume f is,
Integrable or continuous and differentiable?
let's do continuous. Continuous is really
Okay.
nice. Okay, assume f is continuous. Then f is identically 0. And the proof is actually not too bad. You know, imagine not, so that there's some point where, without loss of generality, f of x naught is greater than 0. Then I can find some small delta such that in that region, I'm within epsilon, right? And so in this region, x naught minus delta less than x naught plus delta, we have f of x is greater than, say, 1/2 f of x naught, which is greater than 0. And now what should we do for g?
we can use an indicator function.
I'm sorry?
I was going to suggest we could use like an indicator function that's 1 on the region and 0 elsewhere.
Well, we have to be a little bit careful because we want it to be continuous and differentiable.
You can use a bone function though.
But you know, if this is x naught and this is x naught plus delta, and you take, you know, x naught plus, you know, delta over 2, you could take a function which you know, maybe comes down nicely, something like this. Right. It shouldn't be too bad to come up with a function that will be, you know, 0 by the time you get here and still be differentiable and decaying, you know, well enough so that you're going to be fine. And so what we've been able to do is we've been able to show that, you know, from this information, if we can do this for all g, we deduce that f is identically 0. So the more g we can study, or better yet use, the more we can say about f. You know, imagine, you know, g is even. Then what is true about f? So you imagine we still have this statement over here, but now we're going to assume that we only know this when g is even.
I think f has to be odd then.
So then it's natural to conject then f is odd. So, you know, try to prove that. And so you can see that by having the ability to do this for fewer values of g, we're not going to be able to do the same things about f. The larger the class of g where we know things, the more we can deduce about the function f. Knowing that the function f is identically 0 is much more information than just knowing that the function f is odd. Right?